So now we go to the last talk of this session. So I want to also remind everybody that today we have also a welcome reception in the City Hall. I don't know whether you have received the email or not. We are going to start walking at 5:30 apparently from here towards the City Hall. So the last talk is on...
I'll give them that.
Yeah, sure. Yeah. So the last talk is on compiling control flow in sparse and structured array programs by Willow.
Thank you. Yeah. So thanks for the introduction. I'm Willow. I'm part of Saman's group. We do compilers at MIT. So we'll start with a question. Do sparse array interfaces match the interfaces that we have in the dense world? Another way to think of this slide is like, how should we be programming with sparse arrays? If we can write all these compilers, what's the right interface to say what we want to do? So we, of course, have collectives, right? The NumPy style stuff. And we have ein sums. That's another way we can say how to compute with sparse arrays. We have scheduling, right? So we can use these kind of predefined transforms. Usually they're semantics preserving. That's great if they are. And then there's auto-scheduling or search things. We can do really fancy symbolic stuff, kind of like search for a better program automatically, give it a cost model, tell it what to optimize, right? In this talk, I will advocate that perhaps we should also be able to just directly tell the sparse compiler what to do without considering sparsity or structure, right? So we'll talk about structure as well. Here's my favorite little program. It's a snippet from the Fortran gem. So we start with a little example. It's not gem. It's breadth first search, right? So this is a program that we should be able to express in a sparse compiler. But there's a couple reasons why breadth first search is a little tricky, right? We can't always just write an ein sum. That doesn't get us all the way to where we need to go with like what kind of optimizations we want to do. So the classic BFS, right? We have a frontier. We put our start node on the frontier, and then we iterate over the neighbors of the start node and add them to the next frontier, and we mark them as visited. So we can sort of, like the GraphBLAS folks have kind of convinced us to maybe write this in a different way, which kind of looks like this, where we've sort of, the main change here is that instead of using a stack for the frontier, we're sort of using a sparse array, right? And so now this sparse vector is sort of binary representing in sort of a one-hot way which elements are in the frontier. And most of the work is going on in this expression. So we can take a look. So we can say what kind of optimizations did we need to do to breadth first search? One thing we need to do is direction optimization. So if we're iterating over the adjacency matrix row major, we can't use the mask that we need on the output vector. So that's the not visited mask. So we could do column major, right? So this is like a a loop ordering problem. There's also masking. So we want to be able to fuse the iteration, right? So in addition to just the frontier, we also want to mask on the output. Different direction optimization will have different success with these plans. The other thing that we want to do is we want to early exit. So in the row major case, if each row represents a potential vertex to put on the queue, you can stop as long as you know that it's adjacent to something in the frontier. And so you need to be able to break out of the loop. A couple optimizations that are harder to represent pictorially here is you might want to only consider the structure of your matrix, right? It doesn't matter what the values are. It just matters that there's a non-zero there. And we also want to be able to fuse other calculations into this computation, like the calculation of parents. So I'm spoiling. I didn't expect Saman to be here, but he told me not to spoil. But I'm spoiling this is the code that we write in the compiler that I'm going to talk about, Finch. And so it has the features of what we would like to ask for out of BFS. So we can specify the loop order explicitly, right? We can add conditional masks depending on what kind of masking we need to do. We can mask off computation. We can use user-defined functions, of course. We can also put together multiple statements. So we can mask multiple statements and reuse that kind of control flow that way. We also have a little bit of short circuiting. We represent it a little different than a break, but we can short circuit. And we also have our structured operators, right? If we're going to scatter into the output, we should use a sparse byte map, this kind of thing. And we can achieve a performance that is pretty close to all of the optimizations that Tim Davis has done by hand in the GraphBLAS implementation of this algorithm. So why control flow? Like, why am I obsessed with this? I think that it's a good way to describe at a high level, in a succinct way, what we'd like our sparse computation to do without getting into the nitty-gritty of, like, incrementing pointers over sparse arrays, because that kind of logic is going to be the same every time. So one example is like, consider the computation where we do only the even pairs in a dot product. You could represent this like this. You'd probably get, here's some like pseudocode for like what we'd be doing with a sparse array, right? You want to iterate over the intersection and then filter out all the elements in the intersection. Of course, this wouldn't be a very useful program if we did it verbatim the same way that it works in the dense world, where we iterate over every possible integer and then check the ones that are even and then randomly access the sparse array. So this is sort of the sparsified version of that code. You could also imagine a different strategy where instead we just filter the evens out of A beforehand and then use the evens later, right? And so that would give us an expression that looks a little bit more like this. And of course, you could imagine like introducing a temporary, filter the evens from the temporary. All of these would probably be like better or worse, depending on like how small the intersection is and how expensive filtering is. Here it's pretty cheap. So this, but like I guess this leads us to like a question of like what kinds of control flow do we support, and then on what data structures do we support them? And so this is a hard problem. A lot of existing frameworks try to compromise by focusing on one part of this, right? Halide's popular. It supports many different programs, but only on dense data structures. Taco's a great project. It works on like combinations of dense and sparse tensors, but it doesn't support as many programming constructs, right? It just supports the sort of einsum interface. There's also the Cora compiler. It only works on ragged arrays, but it does combinations of dense and ragged arrays, which are just arrays with different number of elements in every row. And it has a couple features that it supports. You can kind of cheat this if you like limit the scope of the structure to one of the operands, and then use that operand to guide the program. So like essentially just only allowing one argument to be sparse, you can get a wider variety of programming constructs. And so Tai Chi is a much more flexible interface. And then of course we're talking about a compiler that can kind of do both. And this talk is a little bit about what it looks like to do both. So to give an overview of the framework, what we'll do is we'll describe this kind of simple loopy code. And then we have our description of formats, and we put it through a compiler that will reliably take advantage of all of the different structural attributes that you've described in your format description. So we'll talk a little bit about what I mean by structure, because I know I've been using this word, and it generally means beyond sparsity. But I think what I mean by that is that really there's a sort of simplified implementation, simplified representation that uses much less information, right? Sort of like a Kolmogorov complexity of the pattern is less, and we have a format that can kind of compress the pattern. So here's a bunch of examples of structure. We're kind of trying to generalize so that we can capture a little wider variety of these things. So we've seen sparse, but we also have like run length encoding, or you might do a range query or something like that, right? In the case of a range query, we only need like the height and the width of the box, and then what's the value inside the box. So we take pointers from prior work, right? I think we're convinced that we should describe the structure of tensors hierarchically, dimension by dimension. This works for matrices. This is CSR. It works for tensors. This is not quite CSF, but it's like a fun little play on it, right? So maybe you have a dense innermost dimension, and here's our tensor. We also express the structure inside of each dimension hierarchically. So we're using a new intermediate representation called looplets. It allows us to recursively, like hierarchically, describe the structure of the dimension itself, which allows us to kind of generalize to all of these different kinds of structures at each level. This leads us to a question of which levels do we actually need? What kind of structures do we need at each level to be a sufficiently expressive language? So I'm going to propose a couple of properties that I think are worth taking advantage of. This list isn't necessarily complete. Maybe there are more. But maybe we can think of these a little bit more like axioms. So there's sparse, right? Is there a background value? Is it blocked? Is there more than one value, right? Is it sort of representing a range of coordinates or a single coordinate? Then we might ask, are all of those coordinates the same value, or are they different, right? So we have repeated. And then there's also a question of, is there just one structural feature that we're talking about, or is there more than one? And so we call this like a singular property. And if we kind of consider all 16 intersections of whether it's possible to have one or more of these, Not all of them are relevant, right? It doesn't make sense to block a repeated value because we don't know how long the repeats are. And so we still need to store the length of each repeat, and we don't get as much savings from storing, from storing the block. So this leads us to our 8 level formats. Some of these are more familiar than others, but this is sort of the level formats that we're providing the user, and we find that it expresses a pretty wide variety of structure in practice. Some of the new ones that I think are interesting is like you have dense RLE. You might also have sparse RLE if you need to represent more of a mask with like contiguous regions, and we find that sparse RLE is usually the more useful variant. You can also represent, say, our range query, right? We use, if you only have a single run, we call that an interval. If you only have a single point, maybe you're doing a permutation matrix, we call that a pinpoint. And of course, if you only have a single block, we call that a band because it looks like a row of a banded matrix. So to give an example more of the program that it looks like to work with these formats, we'll start with a simple example of just statistics. Suppose we want to compute the sum and the variance, or I guess the mean and the standard deviation of every row of a sparse matrix. We could do it with a program that looks a little bit like this. We'll set up our structures on one side, right? And then we're going to read A once and reuse the value of A with our let statement. So this allows us to do one read, reuse the read, combine multiple updates, and this reads A only once, only accessing the non-zero values. There's a question about, in a program like this, how do all of those structures interact with their various usages as we move through the program? So to do this, we introduce a little bit of scoping, right? We say every statement has a corresponding scope, and loop bodies are going to introduce new scopes. So here, we have these dot equal, which specify tensor declarations. They set everything to 0, and they define the tensor in the scope. And so what we'll do is we'll restrict our structures to be in either a read-only mode or an update-only mode. And this allows us to kind of reinitialize them based on how they're going to be used. So we have a couple functions. There's the declare function. It sort of initializes the tensor to 0. You can freeze it to move from write to read, and you can thaw it to move from read to write. And this, if you can define these functions for all of your levels, then you're good. And we can insert these functions whenever a tensor transitions from being updated to being read from. Of course, this does mean that there's a restriction here, which is that we can't represent programs that recursively modify the same structure within the same loop. And that's kind of by design because the looplets framework doesn't handle that sort of thing. So if our underlying framework doesn't handle it, then it's kind of good that we scoped it out. So we'll go into a couple examples now of what it looks like to program with this kind of a system. So we might imagine 3 approaches to SPMV. There's the row major approach, the column major approach, and a symmetric approach. So in the symmetric approach, we read each value of A, and then we reuse it twice, one for each triangle. And then, of course, we've stored the diagonal separately, so we handle the diagonal at the end. Although you could use if statements to mask off the diagonal, and these have different performance characteristics. But symmetry is a property that is often introduced by the way we use tensor algebra, and so we're going to solve it with a program-level solution to symmetry rather than in the tensor. And we can compare these different implementations of SPMV over many different formats. So this plot is describing which SPMV definition and which structure gave the best performance for these sweet sparse matrices. And we see that we actually get different formats perform better on different kinds of matrices, different column major, different column major or row major, right, might perform better. We see that blocked matrices do perform well on certain sweet sparse matrices, which is not a surprise given that some sweet sparse matrices are very blocked. And then we also see that for Boolean matrices, you should really use a Boolean representation, that sort of a structure-only representation, no values, right? We can also extend our definition of symmetry to multidimensional cases. So here's the symmetric MTTKRP. This is a case where we have many different updates, right? So in this case, we would expect I believe it's, in the 3-dimensional case, it's a 2x speed up, and then we might get a 6x memory bandwidth speed up for reads of A. So here we've read A once, and we've reused it 3 times. We actually get a little register blocking too on B. And then we, of course, have like a separate case for the edge, the tail conditions, right? And then like the body of the work. So we've split it into 2, clean up the diagonals separately. And here we see that we're also able to do some efficient representations of equality. So for these cases, the Finch compiler can actually automatically insert a mask that can sort of wake you up when you hit I equal to k, rather than evaluating every coordinate repetitively. And we see, of course, that we get this n factorial speed up as we increase the number of dimensions, which I think is a sort of a good case that this works. Sometimes we do get a little bit super what we would expect. And I do suspect that this is related perhaps to register blocking and also some of the memory reuse. The last case I'll show is image morphology. So we can program, this kernel is erosion. So essentially what it is that if your pixel is on and all of your neighbors are on, you get to stay on. Right? So this is essentially shrinking the size of the positive blobs in the image. And so for this case, we have a couple of things that are going on here. We're introducing padding, and that's what these coalesce operators are doing, is defining the off positive value, so the out of bounds value. We have these sort of like affine indexes that are occurring. And then, of course, we've unrolled the stencil. So we do left and right, and then we store that into a temporary, and then we reuse that temporary when we compute above and below. And so this is what we chose to measure. You can also imagine doing this on the bitwise variant. So you can change all the operators to work on the bitwise representation as well, and you could represent that like this. So this is the actual program that we are feeding to Finch to get these results. In the bitwise case, you might also want to include a mask in the event that like the entire integer that holds all the bits is 0. Then you can include a mask there, so that you can get an asymptotic performance improvement. And we measured on a couple data sets. The data sets that we chose were like data sets of digits. We have a database of sketches that were drawn by humans, and we have a database that we took from an image processing textbook. And so we see that we get some pretty impressive speedups on erosion if we do 4 iterations compared to OpenCV. One thing that I thought was interesting here is that for some of these data sets, this run length encoding representation is actually the run length encoding representation actually does much better than even the bit packed variant. So it's really data set dependent, right? You do need a compressible image, but if your image is compressible, you can use this sort of sparse RLE format, and you can get a good speed up by restricting computation to the boundaries. So that's all I have for the main talk. In conclusion, I think that we should really make high performance computing easier by being able to say what we want, and then have the compiler follow that high level sketch. There's several papers that contributed to the work in this talk. One of which is a student of mine, Radha Patel, worked a little bit on making a compiler that automates the symmetric transformation I was talking about. You can install Finch. It's a Julia package. So you can install it in Julia. You can install it in Python. We have a Python interface. And I'd also like to make 2 talk advertisements. Jayon will be speaking later this afternoon about extending Finch to continuous indices, to real valued indices. Also, there is a talk on Thursday by Vladimir about formalizing sparse computations, which I think everybody in this audience would probably be interested in. It's in the formalization section, so I felt I should shout it out. All right. Thanks, everybody, for your time.
We have time for one question. Yeah.
If somebody else has a more pressing question, I'm happy to defer. But okay. With the sweet sparse results, was RLE helpful on any of those?
Sweet sparse where?
I think you had a bunch.
SPMV, yes. Yeah. RLE was not as helpful here.
Okay.
And I think that's partially because the the values were different very often, right? Oftentimes it's like they're not, you're not getting like the same value over and over again. Like that really only shows up in cases where that's sort of from the problem introduced as like a constraint or a computer-generated image or one of those sorts of things, yeah. But we do see that the blocked representation does help sometimes. Cool, thank you.
Thank Willow again.